Why are bubbles round? We've all admired bubbles, especially soap bubbles, with their perfectly round shape and shimmery colors. One British scientist, C.V. Boys, was so intrigued that he wrote a 200-page book called Soap Bubbles, Their Colors, and the Forces Which Mold Them. Boys called bubbles magnificent objects, and pointed out that the force that holds bubbles together is present in all liquids. You can't pour tea, turn off a dripping tap, or wade in a pond without encountering it. Imagine filling a balloon with water. The rubbery skin of the balloon stretches and stretches as more water is added. It can only stretch so far, however, until it bursts. Now think about a drop of water. Picture a drop collecting at the end of a faucet. It hangs, growing bigger and bigger. Finally, after it has reached a certain size, it falls off. Why? Boys asked. Does the water hang at the end of the faucet at all? It is as if, he said, the water were hanging in a little elastic bag, like a balloon. Then it is as if the elastic bag breaks or tears away when too much water fills inside. There isn't really a bag around a water drop, but something, Boys said, must be holding the drop together in much the same way as an invisible skin would. This something, a property of water and other liquids, is called surface tension. Take water. Water molecules under the surface are strongly attracted to each other. Surface water molecules, however, are not attracted to air molecules above them. They are only attracted downward and inward, toward the rest of the water. This surface tension creates the effect of a skin on the water. The skin keeps the water hanging on the end of the faucet until finally it gets so heavy it breaks off. Different liquids have skins that are stronger or weaker, Boys pointed out. Alcohol, for example, has a weaker surface tension than water and doesn't form drops as well. But liquid mercury, which skids across the floor in beads from a broken thermometer, has 6 times the surface tension of water. Surface tension also holds soap bubbles together. When you dip a wand into a soapy solution and then pull it out, you see a thin film stretched across the wand. Blow into it, and the surface tension makes the soapy film stretch like an elastic skin. The film closes around the air, and the bubble pops out and it floats away. Because of the elastic skin of a bubble, the air inside a soap bubble is under pressure, like the air inside a balloon. The strength of the pressure depends on how tightly the bubble is curved. The tighter the curve, the smaller the bubble, and the more force on air within. Boys did an experiment that showed that air rushing out of a soap bubble like air jetting out of a balloon can blow out a candle flame. But why is the bubble round? The answer is that the surface tension causes the liquid film to pull itself into the most compact shape possible. The most compact shape in nature is a ball, and not a rectangle, for instance. So the air inside is neatly held in by the same force all around the bubble, at least until the bubble bursts. But, Boys noted, with effort, bubbles can be made that are not perfectly round. For example, if you take a soap bubble between 2 rings and tug on either side, you can pull the bubble into the shape of a cylinder. The bigger such non-round bubbles, the more unstable. A long cylinder will soon develop a waist and break apart into 2 spherical bubbles.